Hey, 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 here we go with our online videos. This section is 5.1a, which is starting off Unit 5. Now, Unit 5 is all about identities. So what we're looking to do is basically replace equivalent statements in order for us to rewrite something or to be able to solve it. So pretty much the whole unit is about being able to use these interchangeable forms of equivalent statements, okay? So that's what we're going to be looking at. Now, if you're looking through your notes, which were posted for you on both MyMathLab and Blackboard, you'll notice over the next several sections, this page, you'll see it over and over and over and over again at the beginning of every single section. And that's because these are the identities we need to be super familiar with in order to complete the problems that we're going to be looking at doing. And I think we're already pretty familiar with our reciprocal identities, right? We know that cotangent is the reciprocal of tangent, so we can write it as 1 over tangent theta, right? So that means that tangent theta is 1 over cotangent theta. Same thing with secant and cosine, and cosecant and sine, right? Secant I can write as 1 over cosine theta. Cosine theta I can write as 1 over secant theta. And something that I notice in a lot of homeworks is that sometimes y'all forget to write the theta in there. Okay, you have to put the angle in because 1 over sec doesn't mean anything if there's not an angle there, all right? Same thing with cosecant. This is the inverse of sine theta, and sine theta is the inverse of cosecant theta. Okay, so definitely want to be really familiar with those if you're not already. You should be, but we're going to go ahead and just keep mentioning them so that we don't forget what we've learned, right? All right, then we want to look at our Pythagorean identities. So we went over these in previous units, right? These are the ones that we get from taking x squared plus y squared equals 1, sorry, not 1, r squared. Thinking unit circle here, x squared plus y squared equals r squared, and solving it by dividing off one of the terms. So if I were to take this statement and I were to divide everything by r, right? Sorry, r squared. If I divide everything by r squared, right, I would have x squared over r squared, I would have y squared over r squared, and then this side would become 1. So that's what's giving us this identity, okay? The sine we get from, the sine squared theta we get from our y squared over r squared. So our other term here would be the x squared over r squared. And x over r, remember, is our cosine. So this would be cosine squared theta. So remember, this was our sin, you confess, you're one with God, right? Remember the ways that we remembered these? Sin, confess, you're one with God, okay? Remember the other one we had was remembering somebody screaming, just give me 1 damn second, right? Or 1 tan second. So 1 plus tangent squared theta equals secant squared theta. And we get this identity if we were to take the Pythagorean the Pythagorean theorem and divide all of the terms by x squared. So if I divide x squared by x squared, that gives me the 1, right? If I divide y squared by x squared, y over x gives us that tangent squared, right? And then r over x gives us secant squared, right? So then we get our last identity by dividing by the thing we haven't divided by yet, right? We've done division by r squared, by x squared. So if we divide by y squared, right? Y squared over y squared is going to give me the 1. X squared over y squared is going to give me cotangent squared theta. And then r over y squared gives me my cosecant. So if you remember from back in the day, right, we said you sin, you confess, and then you're one with God, right? Or the 1 tan second, just give me 1 tan second, right? And then this one, I didn't have anything really clever to remember this one. This was just the 1 cocos, right? 1 plus cotangent squared equals cosecant squared theta. So these are ones that we've already seen, but we need to be a little bit more familiar with because what we can do is we can actually solve these three equations individually for a component of it, right? So I could solve the sine squared plus a cosine squared equals 1 for just sine squared, right? So I'm going to do that, and I'm actually going to use, I didn't really think through the spacing of these notes, so I'm going to kind of use this column of space over here to write these out. So looking at this first one, I'm just going to draw an arrow, right? We have sine squared theta plus cosine squared theta equals 1. Right? And if I wanted to solve that for, say, sine squared theta, I could move my cosine squared theta to the other side by subtracting, right? So that would give me sine squared theta is equal to 1 minus cosine squared theta. Now, that gives us another identity, right? There might be a situation where we want to replace sine squared theta with something, and we could replace it with this, or we could actually go further, because what this is right here is actually a difference of squares. So remember, when we have a difference of squares, something like a squared minus b squared, we can actually factor that, right? Remember good old college algebra factoring here. A difference of squares, if I can identify what the bases are of the two little things being squared, right? So here I have a base a, and here my base would be b that's being squared, then I know this factors into my first base plus my second base, and my first base minus my second base, right? So anytime I have a difference of squares, it factors into the first base plus the second base times the first base minus the second base. So if I apply this little thing to what I have here, right, 1 is a perfect square. My base that I would have to square to get 1 is just 1, right? And then cosine squared theta is a perfect square. And what I would have to square to get cosine squared theta is just cosine theta. So I could rewrite this as sine squared theta is equal to 1 plus cosine theta and 1 minus cosine theta. Okay, so this is another identity that we get from this sine squared plus cosine squared equals 1. Now this is what we got if we solved it for sine squared. We could also solve it for cosine squared, right? So I'm going to go ahead and just make a little squiggly here. I could take sine squared theta plus cosine squared theta equals 1, and I could solve it for cosine squared theta, right? Actually, I'm going to go ahead and let's just squiggly kind of like box this in, okay? And then we'll do the other one. So the other one is if we solve it for cosine squared theta. Now, if I want to solve it for cosine squared theta, I need to move my sine squared theta to the other side. So that would give me cosine squared theta is equal to the 1 that was already on the other side, and then when I move the sine squared term to the other side, I would do that by subtracting. So that would give me minus sine squared theta. And then just like before, this here is going to give me a difference of squares, right? Difference of squares. My base on my first term that's being squared is a 1. My base on my second term would be sine theta, right? So then we could go ahead and factor this one. Cosine theta is equal to 1 plus sine theta and 1 minus sine theta, right? My ones kind of blend in. There we go. Perfect. So notice from that first little Pythagorean identity, we have the original identity that we get, right? Which we need to know. But then we also get two other identities that can be broken down further. So if in one of the problems that we're looking at, we see a 1 minus cosine theta, or maybe a 1 plus sine theta, we could replace that by just taking one of these identities and solving it for the piece we're trying to replace, okay? Now that's true of all of these identities, right? I could do the same thing with 1 plus tangent squared theta, right? I could take this one, 1 plus tangent squared theta equals secant squared theta, and I could solve it for either tangent or secant. So I'm going to go ahead and find the two identities that come from this one. Okay, so if I want to solve it for well, here it's already solved for secant squared theta, right? This one's already solved for secant squared theta. So I don't need to solve it again for this. And this one, when it's solved for secant squared theta, I actually can't go further with it, right? Because 1 plus tangent squared theta is not a difference of squares. Neither one of those is being subtracted. Whereas like the other ones I did, notice I ended up with a subtraction between my two squared terms. Sum of squares does not go further. So this one can't go further. So let's instead solve it for tangent squared theta. So if I solve it for tangent squared theta, I would move my 1 to the other side by subtracting. So I have the secant squared theta that was already there minus 1 that I get from moving this 1 to the other side. Right? Okay, so I move that over, and now we can see that this is a difference of squares. Right? So I can go a little bit further with it. So this time my first base is secant theta, and my second base is a 1. So I can break this down into saying that tangent squared theta is equal to secant theta plus 1 times secant theta minus 1. So that gives us kind of an additional little identity, right? Okay, so I did the first two. So what I would like y'all to do is to take this third one, okay? Notice this third one, right down here, 1 plus cotangent squared theta is equal to cosecant squared theta. Notice this one, it's already solved for cosecant squared theta, right? But I can't go further with this side because it's not a difference of squares. Neither one of them has a negative term. So I can't go further with cosecant. So I want y'all to go ahead and solve this one for cotangent squared theta and come up with the identity. Okay, so go ahead and just pause the video and give that a try. And then whenever you're done, or if you get stuck, play the video and we'll go over it, okay? Okay, let's see how you did. So we're solving for cotangent squared theta, so you move your 1 to the other side by subtracting, and then what you have on the right-hand side is going to be a difference of squares, right? So that factors into cosecant theta plus 1 and cosecant theta minus 1. Make sure when you're writing these cosecant thetas, they're not squared, okay? Because when we modify and rewrite the difference of squares in factored quantities, we have now factored it down, right? So it's no longer a squared, right? It's kind of like when we take an x squared, right, and then we factor it into two quantities, we have an x in each one, right? So make sure that squared is no longer there if you are factoring it down to a difference of squares. Okay. All right. So we have the 3 Pythagorean identities that we definitely need to know, right? All 3 of them are super duper important. And then now we learned that we can go just a little bit further and get an additional 4 properties from these specific ones just by solving them and rewriting it in an equivalent way. Okay. The other 2 are our quotient identities, which we roughly touched on. Tangent, remember, we can use just the ratio. Tangent, normally we use y over x, right? And when we use the unit circle, remember, our y value just becomes sine, and our x value just becomes the cosine value. Excuse me, which means that tangent theta can be rewritten as, whoops, my pen's not working, sine theta over cosine theta, which then also means that cotangent can be written in terms of sine and cosine as well. Cotangent would be cosine theta on top over sine theta on bottom. Okay. All right, so this whole page is full of identities that we need to be aware of. Okay, we need to be able to recall them relatively quickly and know how to rewrite them and rewrite them in their equivalent ways. Okay. The other identities that I want to go over in this first part of 5.1 is our negative angle identities. Okay. So I'm just going to use 30 degrees as an example. Okay. So since we're using our unit circle, we know that if I wanted to find this point right here on the unit circle, this xy coordinate, right? My x would be the cosine value of 30 degrees, and my y would be the sine value of 30 degrees, right? And then we should be able to find sine and cosine of 30 degrees just by using our triangle, right? If I make a triangle for 30 degrees, right? This is 30 degrees. Opposite my 30-degree angle, the length of that side of the triangle should be 1, right? The hypotenuse length of a 30-degree triangle is 2, and then the adjacent side of a 30-degree triangle is square root of 3, right? All right, so if I want to find my sine and my cosine value, our cosine, remember, is our adjacent over hypotenuse. So our adjacent would be square root of 3 over our hypotenuse, which is the square root of 3 over 2, right? And then our sine value is our opposite over our hypotenuse. So opposite 30 would be 1 over my hypotenuse of 2 would give me 1/2, okay? All right, so this is cosine of 30 degrees. So what we're trying to look at is negative angles. So what I want to contrast this with would be, what if we looked for sine and cosine of negative 30 degrees? Okay, so negative 30 degrees means instead of starting at 0 degrees and going counterclockwise, I would start at 0 degrees and go counterclockwise 30 degrees, which would put me here, right? So I could write this angle right here as negative 30 degrees, right? And I'm sorry, this is really small down in here. So then if I wanted to find this point value, right, or this ordered pair on the outside of my unit circle, I could write this as the cosine of negative 30 degrees and the sine of negative 30 degrees, right? So I should be able to find their values using a 30-degree triangle as well. Now, if I were to draw a triangle for this negative 30-degree angle, it should be very similar to the triangle I have above, right? My hypotenuse length is still going to be 2, right? My adjacent side, this x value, is still going to be square root of 3. The only thing that changes is now instead of having a y value that is positive 1, it's going to have a negative 1, right? Because it's in the negative direction and our y is below the x-axis, right? So that's going to change things just a little bit. So if I look at cosine, again, that is, can't hold my pen, adjacent over hypotenuse. So my adjacent side of my negative 30-degree angle is still square root of 3, right, over my hypotenuse, which is still 2. If I look at my sine of negative 30 degrees, we're looking at opposite over hypotenuse. So opposite negative 30-degree angle is a negative 1 over my hypotenuse of 2. So notice what changed. Well, my cosine values didn't change, right? My cosine of 30 degrees is exactly the same as cosine of negative 30 degrees, right? But if I look at my sine values, sine of 30 gave me a positive, sine of negative 30 gave me a negative, okay? So that's kind of indicative, and we can notice here that only the y values are changing. Everything, you know, our x's are staying the same, okay? Only y values change. Okay. Everything else stayed the same. And we can apply this with any angle that we desire. If we wanted to find, say, sine and cosine of 150, and then sine and cosine of negative 150, or sine of 9 and sine of negative 90, right? What we'll notice is only the y values change. So what that does in terms of properties, if I look down here, since the y values are changing, that means that if I take sine of a negative angle, its sine meaning positive or negative, is different, right? The y values change. So this is the same thing as negative sine of the original positive angle. Does that make sense? So if I'm looking at sine of a negative angle, like sine of negative 30, it's the same as if I took the original sine value, which is 1/2, and then just made it negative, okay? But cosine of a negative angle, notice here the cosine values are the same. They don't change. So that means that cosine of negative theta was the same as cosine of positive theta. So we don't need the negative out here because the sign didn't change. Okay. Now, tangent, remember, is a ratio of sine and cosine, right? So I'm just going to come work it out down here. Tangent of negative theta is the same thing as sine of negative theta over cosine of negative theta, right? By definition, we just did this as a identity on the other side, right, of this page. So now that we have this and we know these two identities, we can simplify it a little bit, right? We know that sine of a negative angle is the same thing as negative sine of the original positive angle, right, from this identity we just have. And we know that cosine of a negative angle is the same, right, as cosine of that original angle. Cosine of the original angle, right? So notice what we're ending up with in terms of our original angle. This is the same thing as negative sine theta over cosine theta, right? And sine over cosine is tangent, right? So we're ending up with the negative tangent value of our original angle. So this was just a proof to show that tangent of a negative angle becomes negative tangent of the original positive angle. Okay, so excuse me, let's just think about this. So sine values change. If we change the sine of the angle, it changes the sine value itself from positive to negative, right? Cosine, when we change the sine of the angle, does not change the cosine value. And then because tangent has sine within it, its sine will also change, right? Or its tangent value. And then once we know all of the negative identities, we should be able to find the reciprocal identities as well, right? Because when I do a reciprocal, it doesn't change the sign. So that means since cosecant is related to sine, since sine changed from negative to positive or positive to negative, so will cosecant. So this would be negative cosecant theta. Secant is related to cosine. Notice cosine doesn't change. I don't have to put a negative in front of it. So I also don't have to put a negative in front of secant theta. Right? And the same thing with cotangent. Cotangent does involve the sine value, right? And since the sine value becomes negative, then our cotangent value will also become negative. Okay? So again, this is going to come in handy when we're simplifying problems to know that if we have cosine of a negative angle, it's going to end up being the cosine of the original angle, things like that, just for simplifying purposes. Okay, so these are more identities that we're going to need to know. So basically this whole front and back, first and second page are all the identities we need to know. We need to know the reciprocal identities. We need to know the Pythagorean identities and be able to find the additional 4 from solving for individual pieces of it. We need to know the quotient identities, which you should already know, right? And now, really the only super new thing is our negative angle identities, okay? All right, so I'm going to go ahead and show you just a few example problems of how we can incorporate all these identities, and then we'll stop kind of at this halfway point of 5.1. So there'll be 5.1a and its homework, and then I'll do a separate video for 5.1b and its homework, okay? All right, so this one says if cosine is 5/8, and theta, the angle that we're finding cosine of, right, is in quadrant 4, find each value. Now, anytime they tell you about the quadrant, that's going to tell you the sign of the values we're looking for. Not the sign trigonomic function, but the sign like positive, negative, right? If I want to know if I know what quadrant it's in, I should know if the sine or cosine or tangent value is positive or negative, okay? So the first thing they give us is sine theta. So we're looking for sine theta, and what they gave us was cosine theta. So I need an identity that relates cosine and sine. So if I look back at my identities here, the ones that I have that relate cosine and sine, well, not the reciprocal identities, right? Because sine and cosine aren't reciprocals. So I look at the Pythagorean identities. Sine and cosine, I have this first one, sine squared plus cosine squared equals 1. I also have that sine and cosine, the ratio of the two could give me tangent or cotangent. So it's going to be one of these three that I use, right? Either the Pythagorean identity or one of the tangent cotangent ones. So if I look at this problem, all I'm wanting to do is I'm just wanting to find the value of sine, right? So all I have is a cosine value and we want sine. So looking at the identities that relate sine and cosine, I'm going to want to use this Pythagorean identity, right? I don't want to use either of these because I don't know anything about the tangent or cotangent value. So neither of these are going to help me. So I'm going to choose to use this Pythagorean identity. So I'm going to do part A. I'll do it over here. So we're looking for, let's see, cosine squared theta plus sine squared theta equals 1, right? Actually, I think I wrote that backwards, but it doesn't matter. Sine or cosine doesn't matter which one you write first, but normally we say sin, confess, one with God. So I wrote it opposite. All right, so we have our identity. Now we're going to plug in what we know. What we know is the cosine value. Now this says cosine squared. So I'm going to put in my cosine value, which is 5/8. But since this says cosine squared theta, we're going to have to square that cosine value. Okay, plus sine squared theta equals 1. So I'm going to go ahead and square this value, and then I'm going to move it to the other side. Okay, so if I square 5/8, that gives me 25/64 plus sine squared theta equals 1. And then I'm going to move that 25/64 to the other side by subtracting. So then I'll have sine squared theta is equal to 1 minus 25/64. And then in order to combine these, we can either use a calculator that can do fractions, right? Or we can get a common denominator. 1 is the same thing as 1 over 1, right? So a common denominator for 64 would just be 64. So I can think about this as 1 over 1, and like we're multiplying by 64 on top and bottom. So that means that sine squared theta is equal to 64 over 64 minus 25 over 64. And now we can go ahead and combine the tops. So this tells me that sine squared theta is equal to 39 over 64. Is that right? Yeah. Okay. So now we have it down to sine, but notice part A, it wants sine, not sine squared. So to go to sine from sine squared, we would take the square root of both sides, right? So that means that sine theta is going to equal plus or minus the square root of 39/64. Now, we can't have both a positive and a negative sine value, so that's where our quadrant comes in handy. So we're trying to figure out our sine value. So if we're down here in quadrant 4, right, down here, our y values, or our sine values, right, are going to be negative. So I'm going to go ahead and say this is going to give us a negative sine value. So even though I need to do plus or minus when I'm solving, when I take the square root, since I know it's in quadrant 4, I'm only going to take the negative answer. So that means that sine theta is equal to negative square root of 39 over, now square root of 39 does not simplify, right? That's just 3 times 13, so I can't simplify that. But square root of 64 on bottom, that's a perfect square. So I'm going to go ahead and simplify the bottom. So sine theta is equal to negative square root of 39 over 8. Okay, so that was the first one, and we used that Pythagorean identity. Let's look at the second one. This one wants tangent theta. Okay, so for part B, we want to figure out what tangent theta equals. Okay, so again, we want tangent theta. What was given to us was cosine theta. So we need something that relates cosine and tangent. So again, I'm going to bring my page back over. We're looking for cosine and tangent. Cosine and tangent are not reciprocal identities, so that doesn't help. Cosine and tangent, when I look at my Pythagorean identities, I do have this one, which is not bad, right? Because this is tangent, and even though this is not cosine, it's the reciprocal of cosine. So I could use this second one. That's an option. This one doesn't help me. Or I could use one of these, right? Specifically this one, because I have tangent and I'm given cosine, right? But the difference between this one and that one is that this one requires sine theta, okay? But lucky for us, right, in part A, we just figured out what sine theta is. So here's an option, or here's a situation where you could use either of these. So you could either take this Pythagorean identity and write the secant squared as 1 over cosine squared theta and use it, or you could use this one. And I'm actually going to choose this one just because it seems a little bit easier just to plug in the sine that we just found and the cosine that we were given versus having to deal with squares and square rooting and stuff. So I'm going to use our quotient identity. Okay, our quotient identity says that tangent theta is equal to sine theta over cosine theta. So we just figured out that sine theta is negative square root of 39 over 8. And we would be dividing that by cosine theta, which was given to us, which was 5 over 8. Right? And now we don't want to leave it like that because that's a fraction within a fraction. But remember, fractions just represent division. So this is the same thing as saying negative square root of 39 over 8 divided by 5 over 8, right? And when we divide fractions, we flip and multiply by the reciprocal of the one we're dividing by. So negative square root of 39 over 8 times 8 over 5. And now we can multiply straight across. And before we multiply, I'm going to go ahead and reduce because I have an 8 on top and bottom. So we end up with negative square root of 39 over 5 as our tangent value. So tangent theta is equal to negative square root of 39 over 5. Okay, is that kind of making sense? So really what we're doing is we're trying to take what's given to us and then look at our identities to see which ones do we have that relate to that. Okay. All right. Part C wants us to find secant of negative theta. Now this is a negative identity. So secant relates to cosine, right? And if we look back over here, right, cosine doesn't change value, right? Which means that secant going from a negative angle to a positive angle is not going to change sign, right? So secant of negative theta is exactly the same as secant of just original theta, right? So I'm going to go ahead and write that in. This is the same thing as secant theta, right? Secant theta is related to cosine, right? So I can go ahead and write this. This is the inverse of cosine, so 1 over cosine theta. And then cosine theta is actually what we were given, right? We know that cosine theta is 5 over 8. So this is the same thing as 1 over 5 over 8. And just like we did on this one, right? When we have a fraction on top and bottom, we're just dividing, right? And when we divide fractions, we flip and multiply by the reciprocal. So the one on top stays the same. We multiply by the reciprocal of the bottom, which is 8/5, and we end up with 8/5 as our secant of negative theta value. Okay? Not too bad, maybe? Not the worst thing you've ever seen in life? All right, I want to look at 2 more, and then we'll call it a day. All right? All right, so on this next example, it says we want to write tangent in terms of cosine theta. So again, we're looking for identities that involve tangent and cosine theta. So just like the last problem, right, we were looking for ones that relate tangent and cosine. So I could use this quotient identity, right? But notice it has a sign in there. And this one, we don't have a sign value. So we need something that only relates tangent and cosine. So if I look again, tangent and cosine are not reciprocal identities. That doesn't help me. And I can't use my quotient identities because I don't know anything about the sign value. So the only one that I have that relates tangent and cosine would be this second one, right? Because it has a tangent and it has a secant squared. Now secant is not cosine, but it's the reciprocal of cosine. So I'm going to use this second identity, the second Pythagorean identity, and see if I can rewrite it to solve for tangent theta. Okay, so I'm going to use this identity that says 1/10 second. 1/10 second. So 1 plus tangent squared theta is equal to secant squared theta. So this is the identity that I have, and I'm trying to write tangent in terms of cosine. When it says to write tangent theta, that means I want to solve for tangent theta. I want to say tangent theta equals whatever it equals, right? And I'm hoping that it's written in terms of cosines. So the first thing that I want to do is I want to change this secant squared theta into a cosine, because that's what we're hoping to end up with in our relationship here. So I have 1 plus tangent squared theta is equal to, instead of secant, I'm going to write it as 1 over cosine squared theta. Okay. And then I need to solve it for tangent, because I want to write tangent in a certain way, right? So to get tangent squared theta by itself, I need to move this 1 to the other side. So I have tangent squared theta is equal to 1 over cosine squared theta minus 1, right? Just moving this 1 over to the other side. And then, again, we want to write tangent theta, not tangent squared theta. So to get rid of that squared, we have to take the square root. Okay. So if I take the square root of both sides, I end up with tangent theta is equal to, don't forget your plus or minus, square root of 1 over cosine squared theta minus 1. Right? And I'm actually fine with you stopping here and not going any further, because notice they didn't give us a value to plug in, right? We have tangent written in terms of cosine, meaning we can say tangent theta equals something involving cosine, right? The other thing is it didn't tell us anything about the quadrant. So if they don't tell you what quadrant it's in, we don't actually know if our tangent is positive or negative, so we're going to leave the plus or minus in there. So this is our fully simplified answer. Okay? All right, let's look at one more for this section. This one says we want to write secant theta plus cosecant theta in terms of sine theta and cosine theta. So I first need to find an identity that involves just sine and cosine. So that's not going to be one of the reciprocal identities, right? Because sine and cosine are not reciprocals. We do have a Pythagorean identity, right? This first one, sin, confess you're one with God, right? Sine squared plus cosine squared equals 1. We could use that. The only other one that we have that involves sine and cosine is our quotient identities, right? But the way that we get our quotient identities is dealing with tangent and cotangent. And on this one, it didn't say anything about tangent or cotangent, right? It says that we want to be able, to write secant theta plus cosecant theta in terms of sine theta and cosine theta. And then we want to simplify. So it doesn't say anything about tangent, cotangent. So the identity that I want to use on this one, is I might want to use that squared one, or I can use the idea that these two are actually the reciprocals of what we're hoping to use. right? We want to write this. So whatever it says we want to write, that's what we're starting with. Secant theta plus, cosecant theta. Okay? And we want to write that in terms of sine and cosine, meaning we want to take this and write it so that it only has sine theta and cosine theta in it. So I'm going to use the reciprocal identities. Reciprocal identities. Okay? So we know that this one is related to cosine. We could write that as 1 over cosine theta. And cosecant is related to sine, right? We could write that as 1 over sine theta. Now, unfortunately, in our book, or in our software, a lot of the times we won't let you leave it like that, which is bothersome to me. But they always want it written as like one term. So if I wanted to write this as one fraction, I would need to get a common denominator, right? So just a little refresher. Don't let the trig functions freak you out. This just says we have a fraction with some denominator, and this is a fraction with a different denominator. So it'd be like if I had like 1/7 plus 1/5, right? Just two fractions that I'm adding together that have totally different, unrelated denominators, right? So if I was going to get a common denominator here, we know that the common denominator between 7 and 5 is 35, right? Because basically what we're doing is we're just taking 7 times 5, right, as our common denominator. So we could write this as something over 35, right? And the way that we do that is we just multiply on top and bottom by what each piece is missing, right? And what it's missing is pretty much the other denominator, right? So this would give me a 7 here, and on this one I'd multiply on top and bottom by 5, which would give me 5, right? And then I could go ahead and continue on from there. So I'm sorry, I just have to do it. It just feels so unfinished to just not do it. But I want to do the same thing with sine theta and cosine theta, and that is to get a common denominator. So just like we did over here with our number example, if our denominators are completely unrelated, then my common denominator is just basically taking those two denominators and multiplying them together. So I want to write this as cosine theta sine theta, and I want to write this one as cosine theta sine theta. And then I just need to figure out what do I need to multiply by on top and bottom to create this denominator, right? So on the first one, I would need to multiply on top and bottom by sine theta, right? So that the bottom looks the way I want it to. And on top, sine theta times 1 is just sine theta. And then on the second one, I would have to multiply on top and bottom by cosine theta, right? Because I want to end up with sine cosine theta here, which means I multiply by cosine theta on top and bottom. And 1 times cosine theta is just cosine theta. And now that they have the same denominator, then I can add the tops. So I end up with sine theta plus cosine theta all over cosine theta sine theta. And this is actually as far as we can go. The whole simplifying process from here to here was just so that we could write it as like one term for our answer. Okay. Now, if there was something here that we could simplify, we definitely want to do it. But we don't have any properties for a cosine times a sine. And our properties, our identities, there's nothing I can replace that with. This one almost looks like something I could replace with, right? Because we have that property that says that sine squared plus cosine squared equals 1, right? But in this case, these are not squared terms. So I can't replace that with 1. I can't replace it with 1. Okay, so this is just as far as we can go. All right. Okay, so that is the end of section 5.1a. There will be more to 5.1, but we'll call that 5.1b, and we'll do it in a separate video. So you should now be able to complete the homework assignment for this section. If y'all have any questions, just let me know. I'm happy to help. Okay.